The IRA and other government policies, including the upcoming internal combustion engine bans, are helping to accelerate the decarbonization of the transportation sector. However, we do not have enough domestic production capacity built up for the lithium metal or the metal anodes to support this vehicle growth. We really need to change our trajectory and accelerate the development of a vertically integrated supply chain in North America to meet the demands of the mobility sector.
Your trusted source for information on the energy transition. This is the Insider's Guide to Energy podcast.
Srini, welcome to the show. We're really excited to have you here. We're talking about lithium metal. So first off, in the context of lithium-ion batteries, why is lithium the element that's so important?
Look, lithium is the lightest element that you have and is the key to carrying the charge in your battery. Um, there's so many other technologies that are being developed out there, but the key is the weight and the volume and the energy that the battery brings for a given specific gravimetric and volumetric energy density, right? The one that offers you the lowest mass for that energy density is a lithium ion. The more lithium, there is a set amount of lithium that you can put in a battery before you destabilize it, right? Today, most of that comes from the cathode, and the cathode and the anode are two cages that you have, that the lithium goes from one end to the other as you charge the battery. The cost of a battery now really comes from that cage, right? You cannot take the lithium out, but you can make the cage cheaper, and that is where most of the optimization is happening, is optimizing the cathode or optimizing the anode. And by getting the lithium into that battery in a form that is more readily available and useful, whether it is in the cathode or the anode, makes your battery more efficient. And if you can take a lot of the cage out or lightweight the battery, then you have more range and more energy density in a battery, so the battery in general performs better and can be used for a wider number of applications.
Mhm. Help us visualize that battery. So you talk about a cathode, an anode, a cage, and there's a separator in between, correct? So what's the direction of travel, and why do we need a cage?
Sure. Look, lithium today, in the current generation of lithium ion batteries, you basically have lithium in a cage, and the cage is, you have different norm types of cages. A Tesla would use something called a NCA, nickel cobalt alumina matrix. You also see NMC being used out there, which is nickel, cobalt, manganese. You have something called LFP, lithium iron phosphate. So there are different cages for the cathode right now, and all they are doing is they're hosting the lithium in that cage when you have a battery. And what they do is they stack a cathode, an electrolyte, a separator, an anode, and again they repeat it, right? So you basically, after an anode, again have a separator, electrolyte. So it's back to back stacking, and there are multiple stacks of this, which then they either wind into a cylindrical cell or a pouch cell, and then you have multiple of those connected in series and parallel, and that is what your electric vehicle battery is. Now, in the cathode, it has been optimized, right? When you start, all the lithium today sits in the cathode. The anode is a carbon graphite, and all the electrons sit in the anode. And when you start charging that battery, your lithium moves from the cathode to the anode and then back to the cathode. So it's going across, back and forth, and that is what enables you to charge and discharge the battery. And as you discharge the battery, you're basically using that to either power your device, power your EV, right? That mobility, or your battery being used in a device comes from that capability. Uh, where the industry has spent the most time has been in optimizing the cathode. Where they have not spent much time, and where a lot of the focus today is in optimizing that anode, which is what we refer to as next generation of batteries.
Great. And you're saying that the anode is composed of graphite. So graphite seems to be, I mean, this is what people know as pencil lead. It's abundant. It's cheap. So it why are we talking about optimizing this very cheap, abundant material such as graphite?
Graphite is bulky from a volume standpoint, it is heavy as well. So when you think of what is important in a EV, it is the weight of the battery. And when you talk about the next generation of mobility, which is air transportation, it is the volume that's important. So, from those two aspects, replacing graphite with something that has higher energy density is important.
When I think of an EV battery, I think of many, many cells put together. I think what you just described was at the cell level, correct?
Yep.
And you're talking weight and volume. How much weight and volume are we talking? I mean, what is this significant, or what kind of percentages different can we be? Because a cell is pretty small.
Look, when you think of a cell or a pack itself, right? When you put all these cells together on a energy density basis, on a weight basis, when you replace the graphite with something like lithium metal, you're talking twice the energy density, and on a volume basis, three times the energy density being available when you replace the graphite. So it is substantial, both on a weight and a volume basis.
I might be getting confused. You said lithium sits at the cathode. You're going to replace the graphite anode with more lithium. Can you really have, is that right? You have lithium on both sides?
You can have lithium on both sides. The key question is how much lithium is there on the anode. When you have lithium in the cathode, what you would do is you would use a very, very thin anode, which we call as ultra thin anodes. These could be anything around 2 microns to 5 micron thick. Just for comparison, our hair, the human hair, is about 100 micron thick, right? So you are really talking a 20th of the size of your hair. So a very thin foil being the anode. You're not bringing in a lot of lithium at that point of time into the anode, but just enough to provide a nice plating surface. So the lithium from the cathode, when it comes over, can nicely plate your anode without having any challenges with the deposit. Now, there are certain technologies out there which are called lithium sulfur or lithium air, which really look to replace the entire cathode that you have today with a really cheap cathode like a sulfur or certain other cathode materials which are inexpensive, right? So they take the battery cost down further. But in that case, 100% of the lithium needed needs to come from the anode. So you would end up using thicker lithium foils for those kind of batteries.
Are the changes that we're seeing taking place because of supply chain and getting the materials, or is it just simply because it's a better battery?
Great question. They are two metrics at play here, right? There are two things happening at the same time. You have geopolitical pressures. One, for example, like China recently kind of banned the graphite export out of China, where they are trying to keep a lot of the graphite for domestic use. As we all know, China has about 60% of the EV market. A second need, which is an interesting development, is the Western world is more range sensitive, so they want to have the same kind of a range that a gasoline engine gives them or an internal combustion engine gives them, so where they can go several hundred miles on a single charge, which means either you have to have larger batteries. So if you look at it today, the pack size of a battery in of a EV battery in US is exceeding 80 kilowatt hours, but in China you're more like 40 kilowatt hours. So you have larger batteries being put into the Western world because range is a concern. One way to get that range without putting that much weight into the vehicle is to go to this next generation of batteries, which can lightweight the batteries, give you more energy density.
All right. So energy density is one element. The other thing is how often you can charge and discharge. Do these properties change with the different chemistry?
They do. When you go to the next generation, one of the key metrics that people are looking for these batteries is how quickly can you charge. It's called fast charge. When you are able, the holy grail is 15 to 30-minute charge, giving you a 100-mile range, right? That's what all of the auto OEMs are trying to get
At
to.
what temperature do they do that test at?
Basically these batteries have to work at room temperature, not at elevated temperatures, right? So some of the batteries that are in the market today used in buses do that at elevated temperatures. So the all the R&D work that's ongoing is to bring that temperature down to room temperature operation.
Now, Lye Metals, you focus on anode technology. That's what your company's doing. And you described a very thin membrane of
A foil.
to be a foil. Help me understand more about these foils. I'm interested. I'm curious. So we talked about different materials. Let's talk a little bit about that technology. Where is it today? Are we cutting edge today? Are we bleeding edge today? Or where is it headed?
Sure. Look, think of how the anodes today are, right? The anode is basically a graphite which is deposited onto a copper current collector. So that copper is the foil, and you're depositing a thick layer of graphite on top of that copper. What we are trying to do is use the same copper current collector, but deposit a really thin layer of lithium as a coating surface. The technology that is used is called physical vapor deposition. Physical vapor deposition has existed for several decades and has been widely used for a lot of different materials. A simple example that we see every day is if you open up a bag of chips, you would see the inside of that has aluminum deposit, and that uses physical vapor deposition. So this is large scale, very high throughput kind of a technology that's been evolved. What we are trying to do is adopt that for lithium, which is the challenge because handling lithium is quite different than handling aluminum or some of the other materials. It is very sensitive to moisture, very sensitive to air. So doing it right is what we are bringing to the table. We are basically adopting an existing technology and bringing it into automotive applications.
Oh,
Where we are, to address your second question, where this technology is, we are building the world's largest commercial PVD machine in terms of format, and by format we mean width. Width is a key factor for cost. So for us, with a cost focus, we're building our first machine, which should be available second half of this year.
You mentioned in the graphite anodes that surface area was really important. And I think when you're talking about energy density, it's really charge density, which is related to surface area. So, why is this hard to build foils? And how are you getting that thin layer to actually have high surface area?
So, how are foils made today, right? That's the primary question that I think your viewers need to think of. Today, we make the metal and we provide what we call ingots, right? Ingots are big blocks of lithium metal, anywhere between 3 to 5 kilograms each, that somebody, who wants to make these foils puts into a machine. They are extruded out of the machine, then they are rolled to a certain thickness, right? But this extrusion and rolling has a limitation in that they can go as thin as 25, 30 microns, but typically used for 100 to 200 micron thick foils, right? The challenge is lithium, as you stretch it, starts to tear, starts to rip. So it is difficult to make a very uniform foil. What we do, or this technology with vapor deposition does, is you start from the bottom up, right? So you are depositing on a substrate of copper or polymer and then building your way up. So what we the reason why we say 2 micron is you want a uniform deposit without any pinpricks or holes on your copper. So we what we have noticed is we can do all the way from zero, but you don't get a uniform coat, right? Around 2 micron is where you're getting a uniform surface. And beyond that, up to 20 microns is cost effective. Beyond 20 microns, it starts to get more expensive.
This is a good time for you to tell us about what you think the next generation of batteries are going to be. I think people get a little bit overwhelmed with the alphabet soup of different battery chemistries, the NCA, the NMC, the
Yeah.
LFP, and then there's different, structural components here, as you're mentioning. Where do you think the battery industry is really going in the next 5 years and the next 10?
Look, think of it as this way: there was a battery that was designed with a cathode and an anode. What they realized is cobalt became expensive. So they started to optimize the content of cobalt in the cathode now. That is where this alphabet soup of NCA, NMC, LFP, all of this came, right? But there are two simple pathways where that evolution has happened. One is the high energy density pathway, where nickel, more and more of the N alphabet soup started, or the LFP pathway, which is the iron phosphate, which is the more cost effective pathway, but it does not have the same range or the energy density. So these are the two pathways the cathode has evolved. Now, most of the cathode optimization is done. There is very little tweaks that can be done. So the focus has shifted to the anode. And now you're seeing either silicon or lithium metal start to be introduced in place of graphite to boost the overall energy density in the battery. The holy grail, the end goal, is to have lithium in the anode and completely eliminate the cage with nickel or iron or cobalt completely out, right? So the once you go to that commercialization of lithium metal anodes, and they have been brought into the market, that's when you would see the lithium sulfurs, or basically people going back and completely eliminating the cathode, right? The next step of this evolution is you got to get that anode, graphite anodes, replaced. And once that evolution is complete, you'll go back and start seeing lithium sulfur, lithium air, or some of the other technologies people are talking about.
So, where are the supply chains? Are we talking about domestic manufacturing, domestic supply, and how soon are those factories and other refinery infrastructure? How soon is how soon are the batteries you're talking about going to be built in the United States?
Look, if you look at the market reports and based on customer feedback, people are trying to bring um, capacity for solid state batteries online in this decade, right? Sometime people are talking between 27 to 2030 having gigafactories up and running, right? And it takes 2 to 3 years for a gigafactory to be up and running. So they are already planning right now and getting the funding in place for these gigafactories. Depending on which report you look at, and whether you have an optimistic view or a very conservative view, solid state by 2030 is supposed to be about 200 to 500 gigawatts of capacity. Just for comparison, traditional lithium-ion batteries today have about a thousand gigawatts of capacity. So you're talking about 20 to 50% of that kind of capacity being built out by 2030. So a rapid expansion in solid state capacity. To make this happen, a key is metal and the anodes, right? That is what is lagging right now, because 95, 96% of the metal supply today comes out of China. And so that is what we are working towards, is localizing the supply chain all the way from metal production and anode production in North America. So all our customers who are trying to build this capacity here are IRA compliant.
You mentioned the onshoring of supply chain. You mentioned government support from Canada. Are there other additional support elements coming from the US government, either out of the IRA or other grant programs?
Look, the IRA is very interesting as you scale up, right? The challenge is for small companies which are in the technology development phase, the IRA is not super supportive, right? So once you are above that 50, $100 million kind of a spend range, IRA, DOE funds, DARPA funds, all of these come into play when you're trying to build out that capacity. Where we have struggled is when you are you don't go from lab scale to $100 million plant, right, without the middle step. And that middle step of the funding, you still need industry to help fund those kind of efforts. But once you scale to that $100+ million of capex requirement, the IRA helps. The IRA has been a huge tailwind for next generation battery technologies, right? With the need to onshore. And if you look at the IRA, by 28, 29, 100% of your anodes need to come from US sources if you are trying to get the rebate, right? So it is critical to have policies like that in place.
Let's talk about your personal journey. You have a immense technical depth in talking through all of the different battery chemistries and the internal components. How did you get to the position where you are today?
Sure. It was an interesting journey, right? Because my career is equally split between oil and gas, and the later half being renewable. So I was actually hired into Albemarle in about a decade ago, which was my first exposure to lithium, to really look at lithium as an oil and gas guy, because at that point of time oil and gas was projecting very poor uptake of EVs. It's interesting, right? Now you have ExxonMobil getting into lithium, but back then when you looked at all the oil and gas companies, they were uh, projecting really poor lithium uptake or lithium demand. So that was my first entry into lithium as a non-believer in 2014. And I was asked to really look at this market, really see where Albemarle needs to invest. So my first 2 years with Albemarle was spent looking at all the resources, all the technology, where the market would be, how the demand profile would evolve, what would accelerate, what could decelerate, what are the risks, right? So we built out that data science capability for Albemarle, and really looked at what the market would do. Then that evolved further into the need for recycling, the need for next generation battery technology. So we built out a recycling team, we built out a metal team, we built out solid state electrolyte team. So all of those were where most of this know-how and knowledge came as we built those teams and as we worked with customers. Now Lime Metal offers the ability to really make ultra thin anodes. They offered the ability to really integrate the value chain all the way from metal to these anodes, which when they approached me for that role, to lead this company, I found that very attractive, that there was one player who really realized the value of all this for the US or North American market. And that is what attracted me and brought me to this role.
All right. I always like to end our podcast with a crystal ball prediction. So we're talking about very thin anode technology. Where is that technology a year from now in North America?
I am definitely sure there will be several gigawatts of capacity built out with our technology by 26.
Awesome. Well, I want to thank you for coming on the podcast today. It's been an amazing ride. Thank you for joining us today.
Thanks, Chris. Thanks, Jeff.